Hey, everybody, this is Larry. This is day 15 of the Leetcode Day Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's farm or, yesterday's things going on. I think I heard they fixed it, but I don't know. Let me know in the comments how you made out or if that kind of, messed up your streak or whatever it is that people freaked out about, which, it's fair. Also, you want to see the weekly premium farm? I would do that afterwards because why not, right? I think it just came out today, maybe. Can't tell. So yeah, so definitely hit the subscribe button and the bell for that. Yeah. So definitely hit the bell for that, and let's get started on today, Saturday. The lead code contest is in 2 hours for me, so check that out as well. But yeah, hope everyone's having a great weekend. I'm just kind of chilling, doing my workouts and stuff like that. So I'm kind of tired. Maybe I need to kind of, I don't know, rest more. Anyway, let's take a look at today's farm. 2421, number of good paths. There's a tree, consists of n nodes, and this is actually a high number. So that means that I probably did it in a contest recently, but or maybe not recently. Or for me, everything in the last year is recently, I suppose. But yeah, so there is a tree. Rouse of I is the value of the I know, okay? There's some graphs, and then there's a good path that is a good path is a simple path that has the start node and the end node has the same value. All nodes between the starting node and the end node has less than or equal to the starting node. Return the number of distinct good paths. Okay. I vaguely remember this, to be honest, because I don't think it was that long ago. Okay, so I mean we could also double count it, but it is yeah. I mean I have to, how do I even begin to describe it though? I have some ideas about this, but the first thing is that the observation is that a good path is basically you have two nodes that are the same, and that everything in between, count the number, or everything in between will have equal to a lesser value. The other thing is that this is a tree, meaning that for every two nodes, there's only one distinct path, right? So those are two things that I would start off with. And some of this I feel a little bit unfair, a little bit, just because yesterday's problem was a union find problem, so that's definitely the thing that stuck in my head as well. Is that, or not that, but not that like it's enough. But having union find in my head, it kind of primes me a little bit of thinking like, oh, okay, well if it's maybe I would have thought like, oh, shortest path problem or something like, or dynamic programming, etc. Maybe I would spend a couple minutes exploring those in a contest situation. And if I did this problem recently, you probably can actually look up my contest performance and kind of see what that Larry did during the contest, right? So then you could kind of give you a real look as to how I would solve that problem, and not just like me pretending, or I don't know, whatever, right? With bias or whatever, right? It's me seeing that problem for the first time and solving it. So yeah, so having said all that, knowing that union find is a thing, let me also put it up here. Knowing that union find is a thing, then it becomes a little bit easier. Because now that I could think about that as a way to kind of attack the problem. And the way that I would think about this, I'm just gonna, sorry, my drawing thing is under the monitor, so that's why I'm always like looking for it when I'm looking for it. Okay, there you go. Oops, dropped it almost. Okay, let me put on the thing. Okay. Right, and basically, let me see. The examples are kind of okay, but all right, fine. So basically, you have someone like that, right? And basically the idea that I would think about is there a way that we can process the nodes such that um, the structure will give us the answer incrementally, right? And what I mean by that is that I actually, oh, okay, so the value is one, right? So for example, in this problem, we may say, let's process all the one nodes together, right? So now this node is good, this node is good. How many good paths do we have? None. Okay. Let's say we process the nodes 2. Okay. So here, how many nodes can we do? How many good paths are there? None still. And then next we do 3s. And then now we go, oh, okay, there's one path in these 2. So then now the answer is 1, right? Maybe I misunderstood this. Oh wait, what am I returning? Distinct good paths? Oh, I see. I'm missing the paths where it goes against itself, because I was looking at the example number 1 and it was saying 6. I was like, I don't really. But yeah, but if you count all the individual ones, then let me try again, because this is kind of a terrible example, right? So basically, for example, and I'm going to maybe just do it without number, and then you could kind of process it, randomly or whatever, right? It doesn't even have to be a binary tree, because you're just given edges, right? So yeah. And basically, that's what I would try to do, right? Is that okay? First, for example, maybe I'm going to change the color. Let's say maybe I process this and this, they have the same number, right? Is anything connected? No. And then maybe the next one I process this number and this number and this number, right? And then now, well, now because both of these edges are good, that means that this is connected and this is connected and this is connected, right? So now you have these subcomponents, and then now you ask, okay, well, we just added this one, and this one. How many good paths are there, right? Well, there are 3 things. So then that means that the 3 choose 2. Actually, technically 3. I mean, the 3 choose 2 ways of doing it, right? Which is, of course, just 3 nodes, right? Meaning, this one, you can enumerate the 3 different paths, and of course, technically, I guess it's like, this plus 3, because it connects to itself as well, which is kind of weird. I don't know. Maybe it's fine. I mean, you just have to handle it, right? And then the next one, maybe you handle this one, but then there's no other thing that connects to this. Let me change the color maybe. Let's say we had this one. There's no other thing that connected to this, but even though this is now connected to the thing, right? And then now you process these 2, and yeah, and now you connect this one and this one and this one, and now you have a full tree. There's 2 things in there, so you choose 2, which is you go to 1, and of course plus 2 for whatever reason, right? For the self nodes, and that's basically the idea, right? Is to process these nodes, or sorting them in a way such that you can kind of start from one node at a time, and then kind of incrementally build them up, and then as you kind of think about how this comes about, you kind of see the structure of what you want, right? You're like, okay, well, this becomes a connected components problem. What allows me to solve a connected components problem? And to be honest, for me, sometimes it's a little bit, because even if I knew what I just said, but if I didn't have a data structure to support it, it's useless, right? Like, or maybe I an n-squared data structure or something like this, right? So for me, like, knowing that it's union fine, I'm like, okay, if my thought process would be, and I don't know that this is what I'm advocating, it's just experience and competitive and stuff like this, right? And I'm just trying to disclose what my thought process properly. And I'm like, okay, this union fine, if there's a union fine as a data structure, what can we do, right? And then I kind of come up with what I just said, to be like, okay, now, but I already know that each adding component is simple. We just have to be careful about how to handle, like, maybe you could say edge cases. No pun intended. Maybe a little pun intended. Get it? Edge case. But yeah. So then now we just kind of figure out, like, okay, for example, Um, yeah, and then it's just about keeping track of where everything goes. I think that's basically how I would start doing it. So let's get started. Whew. How would we think about this, right? Okay, I mean, as we said, it's going to be Union Fine. I think Union Fine is, usually a class or two lectures worth in a junior level algorithms class, maybe even more, maybe less. I don't know anymore. So I'm not going to go over it that deeply into like the proofs and stuff like that. It's just going to be more focused on how to use it. Basically, Union Fine, and I'm going to do it from memory, so forgive me if it's incorrect, but n is equal to length of rows, and then you set the parents is equal to I for I in range of n, right? And then now you have two functions. You have the union function and find function. Let's do the find first. And for x, we go, okay, with parent sub. So basically, if parent sub x is equal to x, it means that it is its own parent, meaning that this is the parent of the component. So that's a notation that I use. If it is not, then you could say we return you find of parents of x, right? So then basically you can think about it as a tree, if you will, of parents of nodes, and then you just go up the tree to find the root of the node, because that's one thing that you can maybe say is a normalization, meaning that having that parent most node of this tree, well, you're just basically defining a tree by its root, right? And that's basically the answer. And I know that this looks a little bit funky. Hold on a second. But one thing that you can notice is that, okay, well, in a way, this is kind of like memorization, though you can actually maybe just have an explicit memorization. But the thing is that you can't do a naive memorization. Why? Because as you kind of union things together, the parents of x, or the root of that tree, changes over time, right? So you can't just put a cache on it, because But what you can do is do something called path compression. And basically what that does is that, okay, now, I mean, you can kind of think of it more recursively, but you can just say like, okay, if I'm just trying to find the root, if the parent of my parent, or my, is my grandparent, and I'm always don't really care about my parents at that point, I would care about my grandparent or whatever. So then you can just save it, right? That's basically the idea is about this path compression is you're given a tree of x length, now compress it to one length, right? So that it makes it complexity easier in the future. Again, I'm not going to go over the proof, because it's actually kind of I don't even know how the proof works. I mean, I kind of do, but there's like the path compression and compressed by rank. I usually only do path compression, is usually good enough. There's a lot of literature on it with respect to the inverse Ackermann function and stuff like that. Definitely feel free to read up on it, because that is really outside the scope of what I want. But now we're connecting two nodes together, and then now what do we want to say, right? Basically now, as we say, we find the root of node A, find the root of node B, and then just set one of them to the other's parent, right? So that's basically all you have to do, in theory, right? Because then now every time if you look at all the components of either of those trees or union find trees, each of them, if you go progressively up the tree, it'll be now have the same root, right? So that's basically what you want to do. So UA is you go to U find of A, and UB is you go to U find of B. This is the way that I write it. We have to make some modification a little bit. Right? So that's basically the idea behind union find. There's one more thing that we want to keep track of, maybe, but maybe not. I don't know if I need it for this particular problem, but we'll see. If we need it, we'll get it. And I mean, what I mean is tracking the size. Okay, and this is off memory. I mean, it's honestly 7 lines of code. So, but that said, I have gotten this wrong before on typos, so I don't know. So it depends on how you want to say it. It's not that bad for me, but the idea is also the code is just a byproduct of understanding, right? I mean, you can, and I think that's where people get a little bit backward sometimes. When I mean, it's helpful when you're learning and you try to figure out, there are a lot of things to learn in the beginning, and you just focus on one component, and maybe like, if you have to choose 10 things to learn, maybe it's okay to not have a full understanding if you have an interview like, soon or something, right? I get that. But still, code in code is really just an expression of your understanding and what you want the computer to do, right? And all the things that I was saying to you before, that allows me to kind of come up with it quickly. That's all. Like I don't actually remember this code, and which is why sometimes I get it wrong. Not gonna lie, but I mean, at least in time pressured situation like a contest. But in real life, you have unit testing, and you can fix typos and stuff like that, right? And also you probably just build a library and not have to worry about it. But that's besides the point. But for me, just having the ability to kind of do this helps a lot, right? And also the other part about that is that I get a lot of requests. I know I'm a little bit of a tangent. I get a lot of requests sometimes about like, oh, why don't you write it in C? Why don't you write it in Java? Why don't you write C++, right? And to be honest, I actually can do this in about like 5-6 different languages. But the reason why I'm able to do that in 5-6 different languages, minus some like nuances about memory usage and stuff like that in certain languages, is because I don't memorize the code. I just know what understanding what the algorithm is trying to do, right? And for me, it's not about like all the proofs. Or I mean, obviously, if you have that understanding, it's even better. But it's about the concept that that allows you to kind of know what's going on, right? Like in terms of the visualization about trees and stuff like this. Because when I first learned this, I don't think I've thought about Union Find as trees, to be honest. And but having that kind of, and that's the visualization that works for me. There may be other visualizations that works for you to kind of understand these problems. And that's why I always try to get people to kind of think about this in different ways, and people learn different things in different ways. Okay, anyway, that's a little bit of tension. And then now, what do we want to do, right? Now we want to process these nodes in order, right? So let's say for index x in enumerate rows, right? What do we want to do? Well, let's just have a list of things we want, right? So basically we want, how do you go? Row lookup, maybe? I don't know. Naming things are a lot hard, so I don't know. Maybe this is not a great list. But yeah, and then basically it's just row lookup of x append index, right? Basically with, oh, oops, I said this right thing, but I typed the wrong thing. But yeah, basically now row lookup sub I will mean that all the will contain all the indexes that we care about. Okay. Okay. There's also now it just really depends on how you want to structure the edge list. I know that an edge list is kind of cool, but and maybe we could do it, but now I'm going to do an adjacency list. And hopefully I don't have to go over adjacency list too much, because I think I've done it a lot in the past. And also, this is really deep in the problem. If you don't know adjacency list, probably read up on it, or like just a little bit of graph theory and like representation and stuff like that. But yeah, but now we just set up the list, right? Now we can sort, or now we can process the lookups one by one from the lowest to the highest, right? So how am I going to do that? Okay, so then now for x in row lookup dot keys, but now of course we want to sort it, and I think that's all I need. Yeah. Okay, so that's basically x. We're processing x, and we actually don't care about x per se. I mean, we have to care enough to get the list out of it. But then now, yeah, so processing maybe, or maybe nodes is equal to this. And then now we have to process these nodes. And what does it mean to process these nodes, right? For me, it would be to, For me, it would be just to look at each edge next to it, and from this node, and then see if you could connect them, right? And what I mean by that, you'll see in a second. Hopefully, I don't know. If not, then my apologies. But yeah. So for V in adjacency list of, wait, no, I missed a node. So for U in nodes, for V in adjacency list of U, right? What are we doing? I need more space so it doesn't like order at the bottom of my screen. Okay. So for V in adjacency list, we basically look at route sub V is the index, right? U is the thing. So there are only two scenarios, or well, I guess three, depending on how you want to say it. So either route sub U. So we're processing route sub U, right? So this is which is X. That's what we're processing. So if route sub U, which is all X, but I don't know, maybe I like writing it this way. Okay, fine, let's just do this. If this is bigger than route sub I, or bigger than or equal to, then what does that mean? That means that we can now, you can travel that way, right? You can think about, because if you have to go higher, then there's no path going that way anyway that connects this node of YUX to another in that direction. So basically now, you can union U and V. Okay. Otherwise, we just ignore it. Fair enough, because there's no connecting that edge. And that's pretty much it for this part. And then now, after we connect it, now that we have a new graph of things of connected components, what do we do, right? I think this part's a little bit tricky as well, even though I didn't go over it that much. Or I think I drew it a little bit in the rechoose2 thing, which is still true, right? So now let's just say we have answer is equal to 0. Ooh. Let's just say we have answer, we added by the number of nodes, because these are, nodes connecting to itself. But you can also add n at the end, so maybe I didn't need to do this yet. I mean, I don't know. Okay, fine. I'll just add this to n at the very end. So then I don't have to do it here every time. It looks a little, same thing either way, right? But then then the question is, how many times do you connect to other things, right? So then how do I do that? Well, for each node, we just see what connected component it is in, and how many other nodes. Well, the way that I would think about it in progression is I'll be like, for each connected component, how many of the nodes that we just added are in, right? And from that, you can calculate the answer. I mean, of course, in my case, I go, okay, how many, or for each connected components, how many nodes are there of YUX or whatever? So the other way to think about that is thinking about backwards, right? Which is for each node of YUX, how many what component does it map to, and how many things share that component? So that's basically the idea. Yeah, and you could do it in a couple of ways, but so then let's just say lookup is you go to connections.counter, right? So then for U and nodes again, you find of U, so lookup something like this, and then you could either do the answer adding up later, or you could do the answer adding now. It probably is mostly the same, really. Right, because basically if there is 0 numbers before, then you add 0. If there's 1 number before, then you add 1, so then becomes that 1 2 3 4 5 ... right, or 0 plus 1 plus 2 plus 3, which is in this case going to be n choose 2. So yeah, and I think this is it. Looks good. Let's give it did I miss anything weird? Whatever, just give it a quick submit. Not about, okay, nice. 10,020 day streak. And yeah, what did I do? This is during the contest. I think I remember this one maybe. September 24th. I think I pasted this in and then there was a typo. It was a mess. But so this is where maybe if I just type it out, it would have been faster. But yeah, mostly the ideas are the same though. But yeah, so what's the complexity here? Let's go through it one by one, right? Or through the code. This is linear, so this is already a linear lower bound. It's a tree, so the number of edges is going to be the number of nodes in terms of O of n minus 1, whatever. But O of n, right? Here, this is O of n space already, because for each index, there's one item in the route lookup. Also O of n, I mean, we have a lot of O of n time and space already. However, this is going to be n log n because of this sorting. Look, what are the constraints? I mean, you could say something about some linear sort, but I mean, it's just a regular sort, right? So whatever. N log n, you could say linear sort if you want to do something fancy, but yeah. And then for each node, we look at each adjacency list. So this is going to be O of 1. This one looks a little bit complicated, but as we kind of talked about in the past, hopefully you've been watching a lot. If not, then I apologize. But well, maybe this is the time to hit the subscribe button. But basically, the sum of all the adjacency lists is going to be O of n, right? Or it's going to be 2n because we created 2 edges, or 2n minus 2 if you want to be precise, because we create 2 edges for each actual edge that we started with to go both direction. But so basically, this for loop in total, if you sum all this through all the nodes, it's just going to be O of 2 to the n. Oh, sorry. O of 2 times n, which is O of n, right? So this is going to be linear. Yeah, and also that part goes to this as well. So there's no because each node only gets processed once after the sorting. So pretend that you ignore the sort for now, in that, let's just say you because maybe that makes it look a little bit complicated, but there's no, for example, you could just write something like this, and then, right? And then this becomes clear that this is a linear thing through the sorted key. So this is independent of these things. But even then, it doesn't matter because each node, as I said, even though this is a for loop, each node will only get processed once, and each edge will get only processed twice, one in each direction. And for each edge, it's going to do an O of 1 operation. As I said, ignore the union find things. And then here, same thing as well, right? We do a linear extra space in total because at most each node would only create one thing in the lookup, and yeah, and all these are O of 1s, and again the sum of all the nodes are still going to be O of n. So yeah, so this whole thing, even though the 3 nested for loops, this is actually O of n. You may find that surprising. I am just going to tell you that though. But so yeah, so it ends up being dominated by this sorting of keys, which means that it is going to be O of n log n time, O of n space. Whew. That's all I have for this one. It's really long. Even though I knew how to do it, hopefully I explained it okay, because I spent a long time explaining it, right? I don't know how long I did it in the contest, but I think, well, I know, I mean, I actually did it in the contest pretty quickly, but I just kind of spent a long time because I think this size thing or something weird. I don't know. I don't remember if this is the problem. Maybe there was a different problem. But yeah, in any case, I think I did it pretty quickly in general, but the explanation, there are a lot of components to this problem, so there are a lot of explanations that are needed. Hopefully this was good. And if you watched to here, or if you just skipped to the end anyway, hit the like button again, just to show me some love, I suppose. But that's all I have for today. Well, I guess for this problem anyway, because I'm going to do the weekly problem afterwards, and then maybe the contest problems after that. I don't know how to count, so maybe that's off by 1. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.